Is audio video clear? Today I would like to discuss eigenvalues and eigenvectors. Yesterday I have given introduction. Now the definition of eigenvalues and eigenvectors. Now definition: the roots of characteristic equation, the roots of characteristic equation, determinant of a minus lambda I equal to 0 are known as eigenvalues of matrix A. Eigenvalues of matrix A. Now to each eigenvalue lambda, there exists a non-zero vector x such that a x equal to lambda x, then x is called eigenvector of matrix A corresponding to the eigenvalue lambda. Just I have given the definition. The roots of characteristic equation, determinant of a minus lambda equal to 0 are known as eigenvalues of matrix A. To each eigenvalue lambda, there exists a non-zero vector x such that a x equal to lambda x, then x is called eigenvector of matrix A corresponding to the eigenvalue lambda. There is, if you have idea about the concepts, you can follow. Otherwise, watch the recorded video. Whenever you have completed your backup classes, then you can follow. Okay. Now, yeah, this is the definition. To each, for the roots of characteristic equation are known as eigenvalues. To each eigenvalue lambda, there exists a non-zero vector x such that a x equal to lambda x, then lambda is called eigenvector of matrix A corresponding to the eigenvalue lambda. Lambda is the root, characteristic root or latent root. I'll give the example. Observe. For example, matrix A is a 2 cross 2 matrix 3 1 1 2, for example, or 3 2 1 2, for example. First we have to find out characteristic roots. The characteristic matrix is A minus lambda I. Satish Kumar, it is 100% square matrix. I already told you determinant exists only when matrix is square. Okay? Characteristic matrix is 3, 2, 1, 2 minus lambda I is lambda 0, 0, lambda. Now you will get 3 minus lambda 2, 1, 2 minus lambda. This is characteristic matrix. Now we have to write characteristic equation. The characteristic equation is determinant of A minus lambda equal to 0. Determinant of 3 minus lambda 2, 1, 2 minus lambda equal to 0. That can be written as, by expanding this determinant, 3 minus lambda into 2 minus lambda minus 2 equal to 0. 6 minus 3 lambda minus 2 lambda plus lambda square minus 2 equal to 0. Lambda square minus 5 lambda plus 4 equal to 0. Lambda minus 1 into lambda minus 4 equal to 0. From this, lambda equal to 1, lambda equal to 4. Lambda equal to 1 comma 4. Now lambda equal to 1. Suppose lambda equal to 1, because I have to calculate eigenvector corresponding to lambda equal to 1. Consider A minus 1i of x equal to 0. Put lambda equal to 1 in A minus lambda I. In the place of lambda, substitute 1. 3 minus 1, 2, 2, 2, 1, 1. It is a homogeneous system. To solve this homogeneous system, apply the operation R2 minus 1 by 2 of R1, 2, 2, 0, 0. X1, X2, 0, 0. What is rank? Rank is 1. Number of variables 2. Free variable is 1. So one variable is free variable, right? And now write the equation. The equation is two x1 plus 2x2 equal to 0. Now let us take one variable is k. 2x1 plus 2k equal to 0. x1 equal to minus k. Therefore, x1, x2 is minus k. Take k common. Minus 1, 1. Now, the eigenvector is minus 1, 1. Eigenvector is minus 1, 1. Next, corresponding to eigenvalue 4, we have to calculate eigenvector. Lambda equal to 4. Consider A minus 4i of x equal to 0. Put lambda equal to 4. Put lambda equal to 4 in A minus lambda I. 3 minus 4. minus 1 to 1 2 minus 4 minus 2 1 minus 2. Now apply the operation R2 plus R1 minus 1 to 0 0 x1 x2 0 0. Now what is rank? Rank is number of non-zero rows 1, number of variables 2. Now free variables 2 minus 1 1. Now the equation is first row is non-zero row, minus x1 plus 2x2 equal to 0. Let us take one variable is k, because one variable is free variable. So let us take x2 equal to k. Therefore, minus x1 plus 2k equal to 0, x1 equal to 2k. Minus x1 equal to minus 2k, x1 equal to 2k. Therefore, x1 x2 is 2k k. Take k common, k into 2 1. The eigenvector is 2 1. The eigenvector is 2 1. So in this problem, our matrix is 2 cross 2, 3 2 1 2. We got two eigenvalues, one eigenvalue 1, another eigenvalue 4. Corresponding to eigenvalue 1, we got one eigenvector, that is minus 1 1. Corresponding to eigenvalue 4, the eigenvector is 2 1. Understood? Whether your matrix is 2 cross 2 or 3 cross 3, procedure is same. But in the case of 2 cross 2, one trick is there to calculate eigenvector directly. Observe. So here, lambda equal to 4, consider a minus 4i of x equal to 0. You got a minus 4i. This is a minus 4i. From a minus lambda I, you can take either first row or second row, any one row. Write the equation. The equation is minus x1 plus 2x2 equal to 0. By using first row, I have written this equation. Minus x1 plus 2x2 equal to 0. Okay. Now separate variables. Minus x1 equal to minus 2x2. Okay. Now x1 by minus 2 equal to x2 by minus 1. How? Send right side coefficient left side coefficient right side, like cross multiplication model. Okay. Any cancellation is possible, you cancel. Minus minus you can cancel. So x1 by 2 equal to x2 by 1. From this, you can write eigenvector is 2 1. Understood? Write the equation from a minus lambda I, separate the variables, use cross multiplication procedure, then automatically it generates eigenvector. This trick is applicable only when matrix is 2 cross 2. Understood? Now, Yeah, no need to check rank. Directly write one equation. No. I have mentioned here the trick is applicable only for 2 cross 2. Now, Shantanu, you have written, sir, is it applicable for 3 cross 3 or can we apply this process for 3 cross 3? I have mentioned clearly limitation is 2 cross 2. Understood? Avadesh, your eigenvalue 4. If your eigenvalue 4, whatever eigenvector you are going to get, that eigenvector is corresponding to eigenvalue 4 na? Corresponding to eigenvalue 1. Similarly, you can apply the trick. 2x1 plus 2x2 equal to 0. 2x1 equal to minus 2x2. x1 by minus 2 equal to x2 by 2. After cancellation, x1 by minus 1 equal to x2 by 1. Therefore, the eigenvector is minus 1, 1. Corresponding to eigenvalue 1, the eigenvector is minus 1, 1. पंजाबी आप क्या क्वेश्चन पूछ रहा है किधर eigenvector 0 how eigenvector will be 0 yesterday I have explained clearly 0 vector cannot be eigenvector eigenvalue can be 0 no problem what is wrong in that Nitin, I will explain your logic. Sir, if I take x1 equal to k, I will get my 1 minus 1. Whether 1 minus 1 or minus 1, 1 both represent same vector. Observe. Minus 1, 1. 1 minus 1. This is minus 1, 1. This is 1 minus 1. So the vector minus 1, 1 or 1 minus 1 both lies on the same line. Therefore, they represent same eigenvector. They are not different eigenvectors. Both the eigenvectors are same. Instead of cancelling with minus 1, if you cancel minus 2, then what happened? 1 minus 1 will come. Whether 1 minus 1 or minus 1, 1 both represents same eigenvector. Understood? Now, in eigenvalue concept, सर रैंक 2 आ सकता है किधर आ सकता है कभी नहीं आ सकता 2 क्रॉस 2 मैट्रिक्स के लिए in eigenvalue problems you will get only rank 1 yesterday I have explained you clearly rank of a minus lambda I less than n in eigenvalue problems because determinant value of a minus lambda I equal to 0 understood now just by one example you won't get clarity about eigenvector concept just by one example you can understand how to calculate eigenvalues and eigenvectors but there are different eigenvalues you can calculate eigenvectors very easily if repeated eigenvalue comes then for example the matrix A is 1 1 0 1, for example. Here the characteristic equation is determinant of A minus lambda equal to 0. That implies determinant of 1 minus lambda 1, 0, 1 minus lambda equal to 0. That is 1 minus lambda whole square equal to 0, lambda equal to 1 comma 1. Here we have one eigenvalue repeated 2 times. 1 comma 1 repeated eigenvalue, same eigenvalue. Understood? Got it? Now, corresponding to eigenvalue 1, I have to calculate eigenvector. Consider A minus 1i of x equal to 0. Put lambda equal to 1 in A minus lambda I. 0 1 0 0. What is rank? Rank is 1. Number of variables are 2. Now free variables 2 minus 1 1. The equation is 0x1 plus x2 equal to 0. x2 is 0. Therefore, x1 equal to k. Because one free variable, that free variable is nothing but x1 here. So x1 equal to k. If x1 is k, now x1 x2 is k0. So k multiplied with 1 0. Now the eigenvector is 1 0. The eigenvector is 1 0. Understood? Now in this problem, our matrix is 1 1 0 1. We got two eigenvalues 1 comma 1, but you got only one eigenvector, that is 1 0. Okay, I will give the conclusion after completion of next example. Okay, in this problem you have two repeated eigenvalues. One eigenvalue repeated 2 times, but you got only one eigenvector. Okay, next example. For example, matrix A is 3 0 0 3. Now what are the eigenvalues? The characteristic equation is determinant of A minus lambda equal to 0, determinant of 3 minus lambda 0 0 3 minus lambda equal to 0, 3 minus lambda whole square equal to 0, lambda equal to 3 comma 3. Yeah, in this problem again one eigenvalue repeated 2 times. Okay, corresponding to 3, corresponding to lambda equal to 3, consider A minus 3i of x equal to 0. Put lambda equal to 3 in A minus lambda I. This is A minus lambda I. In the place of lambda, if you put 3, what is the resultant matrix? 0 0 0 0. Now 0 0 0 0, you got null matrix. So what is rank? What is rank? rank is 0. Number of variables 2. Therefore, free variables 2 minus 0, that is 2. Free variables are 2. Do you have any equation? Sir, matrix is null matrix. How to write equation? No equation is available. You can understand that here 2 variables are free variables. So let us take x1 equal to k, x2 equal to t, then x1, x2 equal to kt. This can be written as k multiplied with 1 0 plus t multiplied with 0 1. Any problem? Now the eigenvectors are nothing but 1 0 0 1. This is one eigenvector, this is another eigenvector. 1 minute, observe how these two eigenvectors are created with the help of free variables. The coefficient of k is one eigenvector, the coefficients of t is another eigenvector. Catch my point? The coefficient of k is one eigenvector, coefficient of t is another eigenvector. So you have two free variables k and t. With the help of k you got one eigenvector, with the help of t you got another eigenvector. So number of free variables are 2. That's why you got 2 eigenvectors, independent eigenvectors. Okay, yes. So number of free variables are 2. That's why you got 2 independent eigenvectors. In the previous problem, you have free variable is only 1. That's why you got only 1 eigenvector. Understood? Observe. In the 2 cross 2 matrix 3 0 0 3, eigenvalues are 3 comma 3, eigenvectors are nothing but 1 0 0 1. In this problem, one eigenvalue repeated 2 times. You got 2 independent eigenvectors. In the previous problem, eigenvalue 1 is repeated 2 times, but you got only 1 independent eigenvector. One student has written the comment, sir, for one eigenvalue, how many eigenvectors we have? Okay, first you have to, any student questions like that, first you have to ask him how many eigenvalues you have, whether the eigenvalues are distinct eigenvalues or repeated eigenvalues. Catch my point? If the eigenvalues are distinct, in the given problem, if the eigenvalues are distinct eigenvalues, if eigenvalues are distinct, 1 and 4, 2 distinct eigenvalues, matrix is 2 cross 2. The matrix is 2 cross 2. For 2 cross 2 matrix, eigenvalues are 2, 100%. If n cross n, it has n eigenvalues. I am talking about values, eigenvalues, characteristic roots. Okay. Now, 2 eigenvalues are different, then 100% for one distinct eigenvalue, there will be one distinct independent eigenvector. For every different eigenvalue, there will be one different independent eigenvector. Please remember, suppose if your eigenvalue is repeated, repeated. It is a repeated eigenvalue. I mean same eigenvalues. Then the number of independent eigenvectors are depending on free variables. Here you got one free variable, that's why you got one independent eigenvector. In other case, you have, in the other case, two repeated one eigenvalue is repeated, one eigenvalue is repeated, but you got two independent eigenvectors. The reason is you have two free variables in this problem. That is the logic. Okay. So for any matrix, whether your matrix is 2 cross 2 or 3 cross 3 or 10 cross 10, first you have to check eigenvalues. Suppose your matrix is 3 cross 3, all three eigenvalues are distinct. For every different eigenvalue, there will be one different independent eigenvector, 100%. You need not to check, you need not to write. Suppose if your eigenvalues are repeated, if your eigenvalues are same, then you have to check free variables. Calculate A minus lambda I. Okay, calculate rank of A minus lambda I. So number of free variables here, total number of variables minus rank of A minus lambda I. Please remember, some students commit the mistake here. Sir, you said free variable, that's why total number of variables minus rank. Rank, I said rank only, but that rank is rank of A or rank of A minus lambda I. Here, this rank is rank of A or rank of A minus 3i. Is it rank of A or A minus 3i? Not A, A minus 3i, A minus 3i. So A minus lambda I. Okay. So this free variable, total number of variables minus rank of A minus lambda I gives you idea about, gives you how many number of independent eigenvectors in the case of repeated eigenvalue. Here, while taking rank, some students commit the mistake. How they are going to take rank of original matrix A. Sir, here rank of original matrix is 2. Here we have two free variables, 2 minus 2, 0. Then you will get 0. You should not calculate rank of A. You have to calculate rank of A minus lambda I. Catch my point? Surabhi, very simple. Don't make it complicated. I said very clearly. Observe. If your matrix is 2 cross 2, you have two eigenvalues, lambda 1, lambda 2. Suppose I am coming to 3 cross 3. First, you understand 2 cross 2 first. Without understanding 2 cross 2, sir, explain 3 cross 3. If your eigenvalues are lambda 1, lambda 2, lambda 1 and lambda 2 are distinct. I am talking clearly. Lambda 1 and lambda 2 are different. Then corresponding to lambda 1, there will be one independent eigenvector. Corresponding to lambda 2, there will be one independent eigenvector. Total number of independent eigenvectors are 2. For one eigenvalue, there is one eigenvector. If eigenvalues are distinct, different. Sir, suppose eigenvalues are same. Another case. This is case 1. Okay. Now case 2. Sir, suppose eigenvalues are same. Lambda 1 equal to lambda 2. Okay. So two eigenvalues are repeated. Sir, why to write lambda 1 equal to lambda 2? Lambda comma lambda. Okay. Lambda comma lambda. because matrix is 2 cross 2. So your eigenvalues are lambda and lambda. Now, in this case, I set one trick. What is the trick? Total number of variables minus rank of total number of variables minus rank of, I said A minus lambda I, not rank. Don't write rank. Rank of A minus lambda I. Suppose if you write rank in your notes, you might calculate rank of A. That's why write rank of A minus lambda I. Total number of variables minus rank of A minus lambda I gives you number of independent eigenvectors. How many independent eigenvectors you have? Understand? That is, we are going to write free variables. Catch my point? Now, sir, suppose matrix is 3 cross 3. I am coming to 3 cross 3. In 3 cross 3, you have 3 cases. In 2 cross 2, you have only 2 cases. But in 3 cross 3, you have 3 cases. Why 3 cases? All 3 eigenvalues are different. That is one case. All 3 eigenvalues are repeated. Repeated means same. That is another case. 2 eigenvalues are same. 1 eigenvalue is different. That is third case. Catch my point? All 3 eigenvalues are distinct. All 3 eigenvalues are same. 2 eigenvalues are same. 1 eigenvalue is different. I am going to explain with 3 examples. All 3 different examples. Concentrate. Then only you will get the clarity. After that, I am going to give one definition. Suppose matrix is 3 cross 3 matrix. Matrix is 3 cross 3. 1, 1, 1, 0, 1, 1, 0, 0, 1. Matrix is like this. Now, the characteristic equation is determinant of A minus lambda equal to 0. Determinant of 1 minus lambda 1, 1, 0, 1 minus lambda 1, 0, 0, 1 minus lambda equal to 0. Observe. 1, 1, 1 hoga. Without calculating this also, directly you can say by taking principal diagonal elements, because your matrix is triangular. Okay. Now, 1 minus lambda whole cube equal to 0. Therefore, lambda equal to 1 comma 1 comma 1. So here 3 eigenvalues are 1, 1, 1. Repeated eigenvalues. 1, 1, 1. 1 is repeated 3 times. Okay. Corresponding to eigenvalue 1, we have to calculate eigenvector. Lambda equal to 1. I already told you, consider A minus lambda I of x equal to 0. A minus 1i of x equal to 0. Put lambda equal to 1 in A minus lambda I. Put lambda equal to 1 in A minus lambda I. 1 minus 1, 0, 1, 1. Next, 0, 1 minus 1 is 0. So 0, 0, 1. Next, 0, 0, 1 minus 1, 0, 0, 0, 0. Okay. Now, is it in echelon form? Is it in echelon form? Yes. What is rank? Rank of, I am writing clearly, rank of A minus 1i equal to 2. Number of variables total number of variables 3. Okay, now free variables 3 minus 2 1. So what is conclusion? Instead of solving remaining part, directly you can fix how many eigenvectors you are going to get. How many? One and only one. Sir, why one and only one? I am explaining now. Write the equations. The equations are write equation by using first row and second row. X2 plus x3 equal to 0, x3 equal to 0. By solving these two equations, you are going to get x3 equal to 0 and x2 equal to 0. Since one variable is free variable, that's why let us take x1 equal to k. Therefore, x1, x2, x3 is k0, 0. That is k into 1, 0, 0. Therefore, the eigenvector is 1, 0, 0. Instead of solving the complete remaining part, directly you can understand by checking free variable. In the case of repeated eigenvalues. Okay. So if your eigenvalues are repeated, the number of independent eigenvectors are given by total number of variables minus rank of A minus lambda. Sir, if eigenvalues are different, for every different eigenvalue, there will be one distinct independent eigenvector, 100%. For different eigenvalues, there will be one distinct independent eigenvector. For repeated eigenvalues, total number of variables minus rank of A minus lambda gives you idea about how many independent eigenvectors you have. Okay, next. For example, matrix A is a 3 cross 3 matrix 2 0 1 0 2 1 0 0 3. Nitya, x3 already 0 na? If x3 0 hai to how you are going to take k? x3 value 0, x2 value 0. You should not take x3 equal to k here. You can take only x1 is k because x2, x3 values are already 0. Now, A is 201, 021, 003. Now, the characteristic equation is determinant of A minus lambda equal to 0. Determinant of 2 minus lambda 0 1, 0 2 minus lambda 1, 0 0 3 minus lambda equal to 0. Now Mr. Kamlesh Kumar, where free variables are 0? Two minus lambda whole square into 3 minus lambda equal to 0. Lambda equal to 2 comma 2 comma 3. Please concentrate here. Here, two eigenvalues are same. One eigenvalue is distinct. Corresponding to 2, I am going to find eigenvector. lambda equal to 2. Consider a minus 2y of x equal to 0. Put lambda equal to 2 in a minus lambda I. Put lambda equal to 2 in a minus lambda I. Here 2. Here if you put 2, 0, 0, 1, 0, 0, 1. Okay? If you put 2 here, 0, 0, 1. Okay? Now 0, 0, 1, 0, 0, 1, 0, 0, 1. Is it in echelon form? Is it in echelon form? No, it is not in echelon form. That's why R2 minus R1, R3 minus R1. I'll get 0, 0, 1, 0, 0, 0, 0, 0, 0. X1, X2, X3 equal to 0, 0, 0. Now, rank is rank of a minus 2y is 1. Number of variables, total number of variables are 3. Now, free variables equal to 2. 3 minus 1, 2. So you can understand that here you are going to get 2 independent vectors. Okay, how to get 2 independent vectors? I would like to explain. Observe. First row is non-zero row. Write the equation. Write the equation. X3 equal to 0. The equation is 0x1 plus 0x2 plus x3 equal to 0. So x3 equal to 0. So by using this equation, you can understand that we should not take x3 equal to k, because x3 value already 0 we got from the equation. So two free variables are nothing but x1, x2. Since you have two free variables, that's why I am taking one free variable is k1, another free variable is k2. Let us take x1 equal to k1, x2 equal to k2. Then x1, x2, x3 is k1, k2, 0. You take k1 into 1, 0, 0 plus k2 into 0, 1, 0. Okay, you got two eigenvectors. What are the two eigenvectors? Eigenvectors are nothing but 1, 0, 0, 0, 1, 0. Understood? This concept I have explained you earlier. Writing k1 into something, k2 into something. Where I have explained this concept? Basis. Remember? Basis. So in the basis, whatever members you have, those two in the basis, you are going to write vectors x1, x2, x3. Those are all independent vectors. Catch my point? Here, whatever vectors you got with the help of free variables k1, k2, those two vectors are independent eigenvectors. Independent eigenvectors. Corresponding to repeated eigenvalue 2, you got two independent eigenvectors. So here for 2, 2 comma 2, you got two independent. For 3, 100% one independent, because it is a distinct eigenvalue. That's why compulsory you are going to get one independent eigenvector corresponding to eigenvalue 3. I am going to find out. I would like to explain one trick in the case of 3 cross 3. lambda equal to 3. Consider a minus 3i of x equal to 0. x1, x2, x3. Now, in the place of lambda, substitute 3. What will come? 2 minus 3, minus 1, 0, 1. 0, 2 minus 3 is minus 0, minus 1, 1. 0, 0, 0. That is 0, 0, 0. Now, observe here. You have to reduce a minus 3i into echelon form. You have to write rank, number of variables, free variables, equations, substitution gives you vector. That is one approach. I am not explaining that approach here. I am explaining the trick. Observe. You have 3 rows. 3 rows. In the 3 rows, select 2 non-zero rows. First row and second row are non-zero rows. Catch my point? Now, right. I am not calculating rank, man. Kamalesh, suno idhar. I am not calculating rank. I am explaining the trick. Right. Select 2 non-zero rows from a minus lambda I. I am not applying any operation also. Directly I am selecting 2 non-zero rows from a minus lambda I. Right, middle, last, first, middle. Earlier I have explained middle, last, first, middle. That middle, last, first, middle is different. This is different. Observe. In the 2 non-zero rows, these are the middle elements. Right here. Last, first, again middle. Apply AD minus BC technique. This product minus this product. Tell me, 0 into 1, 0, minus 1, that will become 0 plus 1. This product 0 plus 1. This product 1 minus 0. x3 by 1, x2 by 1, x3 by 1. So eigenvector is nothing but 1, 1, 1. The trick is applicable only for 3 cross 3. I mean this middle, last, first, middle technique. Matrix must be 3 cross 3. Eigenvalue must be distinct eigenvalue. Not for repeated eigenvalue. Understood? Yeah, for 2 cross 2, I have given one trick. Separate the variables, use cross multiplication. For 3 cross 3, middle, last, first, middle. Okay? Now, my question is, sir, if you have 2 repeated eigenvalues and 1 distinct eigenvalue, can you say total number of independent eigenvectors are always 3? Can you say? No. Because if you have a repeated eigenvalue, in the case of repeated eigenvalue, number of independent eigenvectors are depending on free variables. That's why if all eigenvalues are distinct, you can give the conclusion. But if you have repeated eigenvalue comes, you can't give the conclusion directly. After reducing into echelon form, and finding rank of A minus lambda I, comparing with total number of variables, counting excess number of free variables gives us how many number of independent eigenvectors in the case of repeated eigenvalue. Catch my point? One student is posting one comment continuously. Just I have to answer for that. If all eigenvalues are distinct, can we use this trick? Yes. A trick is applicable for distinct eigenvalue means even though you have all three eigenvalues are distinct, you can apply it. Trick is applicable for distinct eigenvalue only. If you have three distinct, you can apply 3 times this trick. For eigenvalue 1, one trick. For eigenvalue, second eigenvalue, once you can apply the trick. Third eigenvalue, you can apply the trick. If all three eigenvalues are different. Understood? Got the idea? Now, I would like to write one definition. Excellent definition. Based on that definition only, the diagonalization or entire eigenspaces concepts can be clarified. Okay, the process of diagonalization is completely depending on these two definitions. Okay, first definition, algebraic multiplicity. Sir, algebraic multiplicity means is a property of matrix. It is not a property of matrix. It is a property of eigenvalue. Algebraic multiplicity of an eigenvalue. Algebraic multiplicity of an eigenvalue. What is algebraic multiplicity of an eigenvalue? Very simple. The number of times, simply I am writing the number of times an eigenvalue is repeated. How many number of times an eigenvalue is repeated, that number of times is known as algebraic multiplicity. For example, A is 5 cross 5 matrix. With eigenvalues, total 5 eigenvalues. In that 5 eigenvalues, 3, 3, 3, 3, 6. Now, what is algebraic multiplicity of eigenvalue 3? Tell me, how many times eigenvalue 3 is repeated? That number is called algebraic multiplicity. How many times eigenvalue 3 is repeated? 4 times. That's why algebraic multiplicity of eigenvalue 3 is 4. What is algebraic multiplicity of eigenvalue 6? Only 1. Understood? Next, geometric multiplicity. Geometric multiplicity, the number of linearly independent eigenvectors, the number of linearly independent eigenvectors of a repeated eigenvalue, a repeated eigenvalue is called geometric multiplicity. Observe here. you just remember this hint. GM is nothing but total number of variables minus rank of A minus lambda I. Okay. Now, sir, it is nothing but free variables, na? Yes. Total number of variables minus rank of A minus lambda I is nothing but free variables. Free variables gives you idea about geometric multiplicity. Why? Because those vectors are generated by k1 into something, k2 into something. So they are, what are k1, k2? K1, k2 are free variables, na? So with the help of free variables, you are going to write eigenvectors. That's why if you count free variables, automatically you will get how many number of independent eigenvectors in the case of repeated eigenvalue. Understood? Now, example. I am taking this example. 1, 1, 1. Yeah, we already solved this example. 0, 1, 1, 0, 0, 1. Okay, here eigenvalues are 1, 1, 1. We already calculated eigenvectors. How many eigenvectors you got in this problem? Only one independent eigenvector we got. 1, 0, 0. Okay. Now, what is algebraic multiplicity of eigenvalue 1? What is algebraic multiplicity of eigenvalue 1? 3. What is geometric multiplicity of eigenvalue 1? What is geometric multiplicity of eigenvalue 1? 1. Understood? Hey, Himanshu, free variable is not giving number of eigenvalues. I have mentioned clearly total number of variables minus rank of A minus I lambda I. Free variables gives you geometric multiplicity. Geometric multiplicity gives you idea about number of independent eigenvectors for the repeated eigenvalue. Understood? Please remember one point. Geometric multiplicity of any eigenvalue less than or equal to algebraic multiplicity of that eigenvalue. GM never be greater than AM in corresponding to any eigenvalue you take. GM is always less than or equal to AM. Sir, when both would be equal? Possibility is there. When GM and AM are equal, just observe this example. Observe this example. Which one? 2 example. Yes. Here, in this problem, eigenvalue 3 is repeated 2 times, not for different eigenvalues. Observe, different eigenvalues AM and GM are equal. For repeated eigenvalues, I am talking about. Here, what is algebraic multiplicity of eigenvalue 3? 2, na? How many independent eigenvectors you got here? 2 independent eigenvectors, na? So geometric multiplicity of eigenvalue 3, 2. Understood? So in this example, GM of eigenvalue 3 is 2, AM of eigenvalue 3 is 2. AM equal to GM. Please remember, for any in your matrix. Suppose your matrix is n cross n. You have n eigenvalues. For all n eigenvalues, AM and GM are equal. Then 100% that matrix is diagonalizable. We will discuss that concept after completion of eigenvalues concept. Okay? In the case of distinct eigenvalues, observe here. In this problem, you have two eigenvalues are here, 1 and 4. What is algebraic multiplicity of eigenvalue 1? 1. Geometric multiplicity of eigenvalue, algebraic multiplicity of eigenvalue 4? 1. Because both are different eigenvalues, therefore only appeared only once. What is eigenvector corresponding to lambda equal to 1? 1 and only one eigenvector. Na? Corresponding to lambda equal to 4? Only one eigenvector. Na? So geometric multiplicity of eigenvalue 1 is 1. Algebraic multiplicity of eigenvalue 1 is 1. Geometric multiplicity of eigenvalue 4 is 1. Algebraic multiplicity of eigenvalue 4 is 1. AM and GM are equal. In any problem, AM equal to GM for each eigenvalue, AM equal to GM for each eigenvalue, that matrix is 100% diagonalizable. Okay, the process of diagonalization and how to diagonalize the matrix we are going to discuss after completion of Cayley-Hamilton theorem. Okay. This is the core concept of matrix theory. If you understand this, you can able to solve any problem. Writing properties and solving problems, no use. You must know concept. If you know the concept, you can able to solve any problem. Okay. Now, observe here. In entire matrix theory, students get confused only at 3 points. One is rank. I'll write. You have to remember. In the examination, if they design the problems, how many number of independent vectors, how many number of independent solutions, how many number of independent eigenvectors? Observe. Number of, NO means number of independent vectors. This is one concept. Number of independent variables. Okay. Third concept is number of independent eigenvectors. Generally, students get confused in these three concepts because of language is similar. So number of independent vectors, number of independent variables. Concentrate here. Number of independent vectors means how many number of independent vectors in your matrix. Matrix is collection of vectors. Whether row vectors or column vectors doesn't matter. Okay, number of independent vectors of a matrix means rank of the matrix. Okay, number of independent variables means nullity. 1 minute, observe. Sir, wait. Because of that free variable concept only, I would like to give the clarity. So please remember, nullity means total number of variables minus rank of matrix A. Sir, earlier you said free variables equal to number of independent eigenvectors. I said free variables equal to number of independent eigenvectors when total number of variables minus rank of A minus lambda I. Here free variables are different, that free variables are different. Please understand. Here free variables are nothing but number of independent variables are nothing but total number of variables minus rank of A. Rank of matrix A, that gives nullity. Okay, this concept, number of independent eigenvector concept. In number of independent eigenvector concept, you are going to write free variables, but these free variables are nothing but total number of variables minus rank of A minus lambda I. Don't get confused between this concept and that concept. You must be clear. If you fix the concept, you never get confused. Very simple. Nullity or number of independent solutions or number of independent variables or dimension of null space is nothing but total number of variables minus rank of A. Now, number of independent eigenvector concept. Because of this vectors and this vectors, some students get confused. Sir, number of independent eigenvectors, they will calculate rank. It is not rank. First, whenever number of independent eigenvector comes, first you have to check your eigenvalues. I am talking about 3x3 matrix. You have three cases. Case 1, case 2, case 3. Eigenvalues are different. Two eigenvalues are same. Suppose eigenvalues are same. Here, two eigenvalues are same. Third eigenvalue is different. Now, same means I have written lambda. Okay. So in this case, number of independent eigenvectors equal to 3. There is no doubt about that. Number of linearly independent eigenvectors equal to 3. Very clear. Because for lambda 1, one eigenvector, for lambda 2 corresponding to lambda 2, one eigenvector, corresponding to lambda 3, another eigenvector. Okay. Now, whenever eigenvalue is repeated, in this case, I am giving the formula. Just you have to calculate geometric multiplicity. GM equal to total number of variables minus rank of A minus lambda I. In the case of third case, you have to be very careful. Corresponding to lambda 2, there is one independent eigenvector. Corresponding to lambda, repeated eigenvalue lambda, you have to calculate geometric multiplicity or free variable, GM. Okay, total number of variables minus, I am writing n, any problem? N minus rank of A minus lambda I. Understood the concept? In entire matrix theory, 90% of the students get confused in these three concepts. Very, very important. Rank concept, nullity concept, number of independent eigenvector concept. Okay, understood? Any queries, any international queries or national queries, you can ask. One student has posted one question. Sir, are the eigenvectors are always independent? The eigenvectors are always independent. That's why they are called independent eigenvectors. Okay. Okay. Now, properties of eigenvalues and eigenvectors. First property, the sum of eigenvalues, the sum of eigenvalues of a matrix, the sum of eigenvalues of a matrix is equal to the trace of the matrix. Calculate GM for lambda, add 1 for lambda 2. Is it right? Calculate GM for lambda. Ah, yes. Gauravi, correct. For different eigenvalue, 100% one independent. You need not think about that. Only when repeated eigenvalue comes, calculate GM. Then how many different eigenvalues you have, that number you add. Okay. Now, the sum of eigenvalues of a matrix is always equal to the trace of the matrix. The trace of the matrix. Sir, what is trace? Sum of leading diagonal elements is called trace. Next property. The product of eigenvalues of a matrix is equal to determinant value of the matrix. Determinant value of the matrix. Third one, if 0 is eigenvalue of A, if 0 is eigenvalue of A, then the matrix is singular. The matrix is singular. Sir, if 0 is eigenvalue of a matrix is singular, suppose matrix is singular, can eigenvalue would be 0? Not all eigenvalues, at least one eigenvalue will be 0. Understood? So 0 is eigenvalue of A, I can write 0 is eigenvalue of A if and only if the matrix is singular. If and only if the matrix is singular. Next point. If all eigenvalues of matrix A are non-zero, if all eigenvalues of matrix A are non-zero, then matrix A is non-singular. Matrix A is non-singular. Okay, next. the eigenvalues of A and A transpose are same. Eigenvalues of A and A transpose are same. Why eigenvalues of A and A transpose are same? Determinant value of A and determinant value of A transpose are same. Determinant of A minus lambda and determinant of A transpose minus lambda are also same. When characteristic polynomials are same, characteristic equations would be same. That's why roots are same. One point I have to clarify. The eigenvalues of A and A transpose are same, but the eigenvectors of A and A transpose are not same. The eigenvectors of A and A transpose are not same. Never be. If eigenvalues of A and A transpose are same, eigenvectors of A and A transpose are not same. Next property. The eigenvalues of A triangular or diagonal matrix, the eigenvalues of a triangular or a diagonal matrix are its leading diagonal elements. The eigenvalues of a triangular or a diagonal matrix are its leading diagonal elements. For example, 1 1 1 0 1 1 0 0 1. Today we have solved this problem. It is a triangular matrix, na? Matrix is triangular. Therefore, eigenvalues are nothing but its leading diagonal elements. Understood? If your matrix is triangular or diagonal, you can take eigenvalues as its leading diagonal elements. Here, some students come up with innovative ideas. I would like to explain one common error about this property. Observe. Sir, matrix is triangular, so eigenvalues are its leading diagonal elements. Suppose if they have given 4 cross 4 matrix. In the case of 4 cross 4 matrix, if the matrix is triangular, you can pick up leading diagonal elements. Sir, matrix is not triangular, but I have applied some operations. Why? Because calculating determinant of A minus lambda equal to 0 for 4 cross 4 matrix consumes time. That's why I have applied operations and reduced it into triangular form. After reducing it to triangular form, shall I pick up principal diagonal elements? Yes or no? Do you understand my question? If your matrix is triangular, okay, you can pick up principal diagonal elements. If the matrix is not triangular, suppose the matrix is 5 cross 5, it is not triangular. I have applied operations and reduced it into triangular form. Finally, I got triangular form. Then I would like to pick up principal diagonal elements. Is that principal diagonal elements are eigenvalues or not? Please remember, you don't know. That is best method. Okay? If you don't know, you can post I don't know. Observe. Those who said yes, they have committed the mistake. Simple. Simple example I'll give. I'm not going to take 10 cross 10 or 6 cross 6, nothing. Just by 2 cross 2, you can cross verify. Observe. Suppose matrix is 4, 2, 2, 4. Okay. I am taking again matrix is 4, 2, 2, 4. Here I am going to calculate eigenvalues with the help of determinant of A minus lambda I. 0. Determinant of 4 minus lambda 2 to 4 minus lambda equal to 0. 4 minus lambda whole square minus 4 equal to 0. 16 minus 8 lambda plus lambda square minus 4 equal to 0. Lambda square minus 8 lambda plus 12 equal to 0. Lambda minus 2 into lambda minus 6 equal to 0. Lambda equal to 2 comma 6. This is the procedure to calculate eigenvalues. Original procedure. We got eigenvalues 2 and 6. Okay. Now, in the next slide, I am going to apply innovative idea. What is that? Applying operations. R2 minus 1 by 2 into R1. 4, 2. Because first row there is no operation. Second row there is an operation. 2 minus 1 by 2 into 4. 2 minus 2, 0. 4 minus 1 by 2 into 2. 4 minus 1, 3. Now, you got triangular form now? Is it triangular form or not? We got triangular form. We got triangular form. Pick up leading diagonal elements. What are the leading diagonal elements? 4 and 3. Can you accept 4 and 3 as eigenvalues? No, not at all. So, what is conclusion? What is conclusion? Is our property is incorrect? Is our property is incorrect? No, property is not incorrect. Property is correct, but we have applied our property in wrong assumption. Okay, applying operations and applying the property is incorrect. Property is correct. Okay, applying operations is incorrect. No, operation is correct, but for eigenvalues applying operations are incorrect. Catch my point? You should not reduce the given matrix into triangular form and the selection of leading diagonal elements is incorrect. If anyone has such type of thought, you must be clear. Okay, understood? So applying operations and selection of eigenvalues is completely incorrect process. One beautiful technique I will tell you. What is product of 4 and 3? Product 12. What is product? 12. Product of eigenvalues same. Here product is 12. Here also product is 12. But this process is incorrect. You should not apply operations to calculate eigenvalues. Understood? This is the determinant value is same. Why? Applying operations. Applying operations. Determinant value does not change. Understood? Now, next property. This is a common error. Next property. If lambda is an eigenvalue, lambda is an eigenvalue of matrix A, then lambda power m is an eigenvalue of matrix A power m. If they are eigenvalues, then trace will be equal. They are not eigenvalues, na Vedant. Lambda is an eigenvalue of matrix A, then lambda power m is eigenvalue of matrix A power m. You have 9 properties, 8 or 9 properties. Observe. K lambda is an eigenvalue of matrix Ka, where K is a scalar. Okay, next, third property. Lambda plus K is an eigenvalue of A plus Ki. Fourth property. Lambda minus K is an eigenvalue of A minus Ki. Next, fifth property. Lambda square plus A1 lambda plus A2 is an eigenvalue of A square plus A1A plus A2I. Next, sixth property. 1 by lambda is an eigenvalue of matrix A inverse. Next property. Det A by lambda is an eigenvalue of matrix adjoint A. 1, 2, 3, 4, 5, 6, 7. K. The matrix, if A is a nilpotent matrix, then if A is a nilpotent matrix of order n, then all its eigenvalues are 0. Then all its eigenvalues are 0. Suppose your matrix is a nilpotent matrix, each eigenvalue of a nilpotent matrix is 0. Sir, what is nilpotent? I have explained in the first lecture. A power A is non-zero matrix, A square is non-zero, A cube is non-zero. Suppose A power 4 is 0. Then that is nilpotent matrix of index 4. If your matrix is nilpotent, every eigenvalue of nilpotent matrix is 0. There is no non-zero eigenvalue for nilpotent matrix. Next property. The eigenvectors of A inverse, A adjoint of A square, A cube, A power 4, and so on. Eigenvectors of A inverse, adjoint A square, A cube, and so on are always same. Eigenvectors are same, values are not same. In the case of A inverse, adjoint A square, and so on, eigenvectors are same. What about A and A transpose? Eigen values are same. In the case of A and A transpose, vectors are not same. Here, vectors are same, values are not same. Remember like that. Next. In a matrix, if n rows are identical, in a matrix if n rows are identical, then n minus 1 eigenvalues will be 0. In a matrix, if n rows are identical, 100% n minus 1 eigenvalues will be 0. For example, matrix is 2 cross 2. How many rows are identical? 2 rows are identical. Compulsory one eigenvalue 0, another eigenvalue 2. Suppose if your matrix is 3 cross 3, how many rows are identical? 3 rows are identical. If 3 rows are identical, compulsory 2 eigenvalues are 0. Third eigenvalue will be 3. Sir, how you got third eigenvalue? With the help of trace, you can find out. Otherwise, we have one beautiful technique. Observe here. Sum of all elements of first row. What is sum? 4 plus 2, 6 na? Sum of all elements of second row, 6. Please remember, sum of all elements of each row, every row is same. That sum would be one of the eigenvalue. Here, sum of all elements of first row is 6. Sum of all elements of second row is 6. Therefore, 6 is compulsory one of the eigenvalue. That is a trick. So, based on the trick, you can identify here. Sum of all elements of first row 2, sum of all elements of second row 2. Therefore, 2 is compulsory one of the eigenvalue. I said sum of all elements of each row. Each row means every row. Sir, 2 rows equal, third row different. Can we take? We should not take. Each row, if sum is different, logic is not applicable. Trick is not applicable. If sum of all elements of each row, every row is same, you can pick up that sum as one of the eigenvalue. Only one eigenvalue you can get by using this trick. Here, sum of all elements of first row 3, sum of all elements of second row 3, third row 3. Therefore, 3 is one of the eigenvalue. Understood? Suppose your matrix is 4 cross 4. What are the eigenvalues? 4 rows are identical. Therefore, 3 eigenvalues are 0. One eigenvalue 4. Understand? Now, next property. Next property. If A plus IB is an eigenvalue of matrix A. If A plus IB is an eigenvalue of matrix A, then compulsory A minus IB is also an eigenvalue of A. If A plus IB is one of the eigenvalue, compulsory A minus IB is also another eigenvalue of matrix A. Next property. I have explained you about Hermitian, skew Hermitian, unitary matrix in the first lecture or second lecture. Remember? Based on transgate operation. Okay. Now, properties. The eigenvalues of a real symmetric matrix or a Hermitian matrix. The eigenvalues of a real symmetric matrix or a Hermitian matrix are always real. Next, the eigenvalues of a skew symmetric matrix or a skew Hermitian matrix a skew symmetric or a skew Hermitian are either zero or purely imaginary, either zero or purely imaginary. Third one, the eigenvalues of an orthogonal matrix are a unitary matrix. An orthogonal matrix or a unitary matrix have absolute value 1. Absolute value 1. Sir, what is absolute value? Modulus value 1. If lambda is eigenvalue of orthogonal matrix or a unitary matrix, mod lambda equal to 1. I have to give little bit clarity about this third property, this property, this property. Why I have to give the clarity? Most of the students get confused about this property. What do you mean by absolute value 1? Sir, mod lambda equal to 1. I have written already. Imam Basha, 1 and minus 1 are possible. Always 1, plus 1 or plus 1 minus 1. That's why I would like to give the clarity. Not only 1 and minus 1. What about I? What about I? I minus I. What is length of I? 1. Minus I, 1. Please remember. Mod lambda equal to 1 means length of that eigenvalue is 1. For example, the eigenvalue lambda equal to minus 1 by 2 plus I root 3 by 2. Sir, lambda equal to minus 1 by 2 plus I root 3 by 2 can be an eigenvalue of unitary matrix or not? Possible. Why? Because if you calculate length mod lambda square root of minus 1 by 2 whole square plus root 3 by 2 whole square root of 1 by 4 plus 3 by 4, square root of 4 by 4, 1. Mod lambda is 1. Possible or not? Possible. That's why you have to remember circle concept, unit circle concept. In the case of Hermitian, skew Hermitian, unitary, whenever if you have any confusion, better to go for circle concept. Okay? Observe here. What is circle concept? This is unit circle. Unit circle. Mod z equal to 1. Okay? Now, I am using for real line, I mean x-axis, I am using one color. For y-axis, I am using another color. For circle, another color. Okay, just for your convenience. Please remember the eigenvalues of Hermitian matrix and symmetric matrix are always real. This is real line. This is imaginary line. This is unit circle. Please remember, eigenvalues of symmetric and Hermitian are always real. So, if your matrix is Hermitian, or symmetric, those eigenvalues always lies on the real line. Real line. Okay. Next. Skew Hermitian or skew symmetric. Eigenvalues of skew Hermitian or skew symmetric are always lies on the red color, imaginary line. Sir, 0 can be eigenvalue of Hermitian? Yes. 0 can be eigenvalue of skew Hermitian? Yes. Because point of intersection. Na? Catch my point? This is 0. Na? Now, what about this point? This point 1. This point minus 1. This point I. This point minus I. So please observe intersection points. Intersection points. White color circle intersects green color at 1 and minus 1. So 1 and minus 1 can be eigenvalues of Hermitian, skew Hermitian, or orthogonal or unitary. Understood? Eigenvalues of orthogonal and unitary lies on the unit circle. Modulus of lambda 1 means magnitude 1 means all the eigenvalues lies on the unit circle. Eigenvalues of orthogonal and unitary lies on the unit circle. Catch my point? Because sometimes in previous gate papers, when you observe 1 plus I, okay, or 1 by 2 plus I root 3 by 2 is eigenvalue of which of the following matrices? Option A, unitary. Option B, singular. Option C, skew Hermitian. Option D, orthogonal matrix. Like that, any such type of question is given, just identify that eigenvalue in the circle concept, whether it lies on the boundary of the circle or on the real line or imaginary line. Based on that, you can answer the question very easily. Understood? Now, next property. Example bata do. All the examples will come when you remember the properties. Why I am giving the properties today? Tomorrow you have no class. Next class is on Monday. What you have to do? You have to read all the properties. You have to memorize. You have to remember. If you remember all the properties, you can easily solve the problems. That's why I am covering all the properties today. Okay, next property. The eigenvectors corresponding to distinct eigenvalues, the eigenvectors corresponding to distinct eigenvalues of any square matrix are always linearly independent. Example I have already given here. If the matrix is square, all eigenvalues are distinct. In this problem, matrix is square, eigenvalues are distinct, then eigenvectors, one eigenvector is -1 1, another eigenvector is 2 1. Observe this example. Matrix is 3 2 1 2. Matrix is 3 2 1 2. Eigenvalues are 1 and 4. Both are distinct eigenvalues. Eigenvectors -1 1, 2 1. You have already calculated. Now, I have to prove that these eigenvectors are linearly independent. Verify. Arrange these two vectors in a matrix. Calculate determinant value. 0 or non-zero? Non-zero. Therefore, they are linearly independent. Understood? Eigenvectors are linearly independent. I have calculated, I have arranged eigenvectors in a matrix. I have calculated determinant value. I found that non-zero. Therefore, they are linearly independent. Understood? Next. The eigenvectors corresponding to repeated eigenvalues of any square matrix may be or may be linearly dependent. Eigenvectors corresponding to repeated eigenvalues of any square matrix may be linearly independent or may be linearly dependent. Nandini, I am coming to your question. Come here. In the case of repeated eigenvalues, you have here only one independent eigenvector. One independent eigenvector, but you have three eigenvalues na. One eigenvalue repeated 3 times na. What about one independent, What about remaining? Remaining are dependent. One and only one independent. Remaining are dependent. That's why overall set is dependent. That is the logic. In this case, in the case of repeated eigenvalues 3 comma 3, in the case of repeated eigenvalues 3 comma 3, you have two independent. If you arrange 1 0 0 1 in a matrix, determinant value non-zero. Understood? So if your matrix is n cross n, if you have n independent eigenvectors, then set is independent. In the case of repeated eigenvalues, my discussion, in the case of repeated eigenvalues, if you have 3 repeated, if 3 independent comes, then set is independent. Suppose in the case of 3 repeated eigenvalues, if you get one and only one independent, the remaining are dependent. The set is dependent or independent? Set is dependent. That is the point here. Okay? So, in the case of the eigenvectors corresponding to the repeated eigenvalues of any square matrix may be independent or may be dependent. That's why there is a concept known as geometric multiplicity. So in the case of repeated eigenvalues, you have to check geometric multiplicity. If geometric multiplicity is equal to algebraic multiplicity, then the set is independent. If GM is less than AM, if GM is less than AM, whatever difference you have, that number of dependent. That's why the set is dependent. Catch my point? Today we have covered entire concept of eigenvalues and eigenvectors. 2-3 properties are there. We can discuss in the next lecture. So what you have to do, you have to revise each and every property. You have to remember all the properties. You have to remember. Okay. So all the problems related to this eigenvectors and eigenvalue concept, I'll be discussing on Monday. Okay. Thank you. Please revise. Otherwise, there is a chance to forget the properties. Revise as many times as possible. Right. Thank you.